Everyone, welcome to the collaborative event between the University Graduate School of Science and Engineering in the concept of grad talks and a collaboration with the IEEE Distinguished Lecturer Program. We honorably host Professor Jian San from RPI, Venezuela Political Institute, and also Professor Mehmet Ali Özçelik, who is also the head of IEEE PELS Power Electronic Society Turkey Chapter Chair. And now, first of all, I want to introduce Mehmet Ali Özçelik. Professor Özçelik will tell us briefly what IEEE Power Electronic Society does. About the activities, and afterwards I will introduce Professor Jian San for his speech. Yes, Professor, that's your turn.
Okay, hello. Hello everyone, my name is Mehmet Ali Özçelik. We set up chair, Power Electronic Society chair at end of the 2020, and IEEE Power Electronic Society has official website is IEEE.org, and the purpose of the Power Electronic Society is make a connection area of the power electronic. So I have a presentation for this. Let me share the screen now. Yeah. Using for the IEEE.org website, you can see the information about the chapter, and this is a non-profit organization, IEEE, and IEEE, you know, largest professional association in the world, and it dedicated to advancing technology, innovation, and excellence for the benefit of the humanity. The chapter was founded in 1987 after the few years of operation as the Power Electronics Councils. Now, the past chapter has over the 9,000 members on the world. Now, President is reaching change, and we have membership benefit include publication like our IEEE Power Electronic Magazine and open online subscription, IEEE Power Electronics letters, transaction on power electronics, and a journal of emerging and selected topics on power electronics, and IEEE Electrification magazine. And you can also access the conference proceeding on the website. And in the October 2019 launched IEEE Open Access Journal of Power Electronics. We have benefit for the membership. Benefit include conference workshop. You have registration discount on the conference, samples on the workshop, and with the resource centers, you can access a multimedia online library that is free for the all members. And there are a lot of technical community under the chapters, like this power control core technologies, power conversion system, motor drives and actuators, vehicle and transportation system, system and energy system, high performance and emerging technologies, and communication energy system. The networking of the past chapters has over the 170 chapters worldwide, including professional student branch. And we have distinguished lecturer program. With this program, you can invite online and physically distinguished lectures. only you need fill out this form on the website. PAS also has broad student program and support exciting students activities like IEEE Future Energy Challenge, student travel grants, mentorship, PAS prize, thesis, talk. And also PAS is working about the standards and driving force behind the international technology roadmap for wide power semiconductors and numerous standards, activities relating power electronics and smart grid initiatives. And you can join PAS today and connect it to ultimate in source of power in your industry. And for the students, we have a promote code. We can share it. Now I will give talk to Professor Dr. Jian. He is from the Rensselaer Polytechnic and he is director of the Center for Future Energy System. He is also vice president of the conference to Power Electronic Society, and thank you. He joined us today.
Thank you very much, Professor. Maybe you can stop sharing the screen so that Professor Jian can share it in an easy way. By the way, when the screen is prepared, I can give a bit more information about Professor Jian. Professor Jian's son received his doctoral engineering degree from the University of Paderborn, Germany. And before joining the faculty at Rensselaer RPI in 2002, he was a principal engineer at the Advanced Technology Center of Rockwell College, where he worked for 5 years. And he's currently a professor of the Electrical, Computer and Systems Engineering Department and director of the Center for Future Neurosystems funded by the New York State government. As a son, Professor Son is a fellow of IEEE and is active in the IEEE Power Electronics Society. He was the editor-in-chief of IEEE Power Electronics letter. That's the famous letters, actually, from
2008 to 2014. And he's currently the treasurer and a distinguished lecturer of Power Electronics Society in IEEE. He also received several awards from the IEEE Power Electronics Society, including the Modeling and Control Technical Advancements Award in 2013 and our David Middlebrook Achievement Award in 2017. He has more than 200 publications and holds 11 US patents and 1 European patent. Professor Jian, we are very glad to host you here physically and always electronically. And we are excitedly waiting for listening to you. Thank you very much.
Great, Professor Ozan, thanks for the introduction, and Mohammed, thanks for the making arrangement. It's my second trip to Turkey. So very interesting. Last time I was in Istanbul also. University, Sabancı University organized an energy workshop in September 2019, and they invited a bunch of people. So I was in Istanbul for a couple of days, but this is a very interesting city to visit. Before I start with my presentation, maybe I just reiterate some of the points that Mohammed made about PELS. You know, we're here to represent the Power Electronics Society, and I know many of you are probably already members of IEEE. There is a lot of benefit to join individual societies like PES or PELS. So Mohammed mentioned some of the benefits. I hope you pay attention to it. Particularly for students, we have some promotion going now. So if you're already an IEEE member, you can become a PELS member for free. And if you are interested, Mohammed can give you the promotion code. You just go to the IEEE webpage, you put in the promotion code, you will become a member of Power Electronics Society. as well at same time, and there's no limit right now. Normally the promotion will be good for 1 year, but right now we're kind of running that continuously because the society has been doing very well financially. We got so much money, we really don't need to charge people to join the society. So that's easier process. I hope you will consider to become a member of the PALS. The additional benefits, including I think there might be an interesting difference between PALS and the PES. I'm also a PES member, but for PES, you don't get a free access to the publications. Right? So you have to subscribe to the publication in journals separately. If the university has access to IEEE, it may not be a big deal. But your individual membership doesn't give you access to the PES publications, other than the magazine, which is not really technical. Right? PALS, on the other side, we give every member access to our publications. So the IEEE Transactional Power Electronics, for example, the JASP, the Journal on Emerging and the Selected Topic in Power Electronics, and a couple other transactions, they are all freely available to every member. So if you become a member, you can download all those papers, as well as all the conference proceedings. So because I think we started out to be a smaller society, we didn't feel, we will give out too much by giving people the access to the publications. So they become a tradition for us. PES, on the other hand, is a larger society. They used to have many more publications. So I think they want to have a better controlled access. But PES, PALS, it's a great benefit. If you want to download papers in Power Electronics, all the transactions, conferences, your membership will give you access to that. So that's an interesting difference. Obviously, beyond that, you get an additional discount if you go to a PALS conferences. And I actually have a page showing all the conference we run. Maybe I start to share the screen first. So because I'm the vice president for conferences, I kind of have to take responsibility for all our conferences. So this diagram shows all the conferences that Power Electronics Society runs. So at the top, you see the so-called ECCE, that's Energy Conversion and Energy Conversion Congress and Exhibition, so ECCE, and we run that in North America, in Asia, in Europe. So this kind of conference series in different continents, like the smart grid meeting of the PES Society, right? We have that also in different continents. So these conferences are annual in different continents. And then APEC, the Applied Power Electronics Conference, has like 30 years of history. It's every year, but it's normally in the US, or has always been in the US. SPEC is the Southern Power Electronics Conference. It's a relatively new conference. It was designed to be on the Southern Hemisphere. So, South America, Pacific, and South Africa. So these are the society level conferences. And then underneath, we have more conferences organized by the so-called TC, technical committees. There's so many, I cannot name, but, we got 11 or 12 TCs, and they all have these individual conferences. So there's a lot of conferences. And I joke with people, if I want to go to all the conferences, I wouldn't be home the whole year, because we got a 40-some conference every year to run. So being able to access all the proceedings and receive discount when you register is another benefit. On top of that, having the DL program and others will also be of interest to you, hopefully. So just add to Mohammed's comments about the benefits. Hopefully, we can see more PALS membership and activities in the area. If you have any questions, please feel free to reach out to Mohammed. Let me get to my presentation. Right. So the technical talk I prepared for today has to do with power electronics application power systems. And I know your university has a very strong power systems program. So I hope this will be of interest to you, because power electronics is kind of my own expertise. Professor Ozang introduced me before. I worked at the Rockwell Collins for 5 years. I did all these kind of power converters, building hardware for different applications, for aircraft, different applications. But about 15 years ago, I decided to extend more into the power system application of power. So it's still power electronics, but for power system application. And a lot of that has to do with renewable energy. You heard about wind turbines, PV inverters, HVDC transmission. So these are all power electronics devices that I work on. But more and more I'm getting into the system aspect. So still, keep my feet on the power electronics side, but I'm reaching out to the system more and more, because it's necessary now. It's really becoming necessary because of the transition of what we call energy transition that you heard in the news. So my talk is about really trying to connect the two fields. And I spoke with Mehmet a few times. I thought this is a great opportunity for many power programs. I think in US, in other universities, power electronic power system, both fell under the power system program. We're supposed to be like, brothers and sisters, right? And I think it's really become necessary now to interact closely. So that's kind of the topic, and I'm aware of the time, so I'll try to finish in 40 minutes, and hopefully we can have some discussions. I'm going to skip this page outline. So if you haven't studied power electronics, so this is just a quick introduction of what power electronics is about. In essence, power electronics is about conversion of electrical power using electronics, right? So semiconductor devices, that's called electronics, but we use semiconductor devices to perform energy power conversion. That's power electronics. So if you look at the form of power conversion, right, basically convert electric power from one form to the other. Right, so the diagram shows you can go from DC, one DC voltage to the other, another DC voltage, from DC to AC, AC to another form of AC, so different frequency, and the AC to DC. So this kind of diagram shows all the different functions that power electronics provide. But obviously, behind each function, there are many applications. In terms of power system, so the application of power electronics is very broad. You open your cell phone, you probably find, I would say, 20 DC-DC converters in there, because of the different chips, regulating DC voltage, managing the battery. Same in the laptop, electrical vehicle, you heard about it, right? The chargers, the drivetrain, it's all power electronics, basically. But what I want to discuss today is more for the power system application. So more in the generation and transmission instead of the consumption side. So this is a kind of one of the charts. So in the power system, right, we divide the system into generation, transmission, distribution, consumption. Up to a decade ago, the application of power electronics had been limited mostly to the consumption side. I mentioned electronics, solid state lighting. I think these look like LED light bulbs, right? Electronic devices, motor drives. You need power converters to do the power conversion. So most of that is on the consumption side. There are some application at the distribution transmission level. The diagram on the bottom shows, for example, some of you may recognize these let me turn on my laser point. So some of you may recognize that this diagram shows HVDC transmission station, right? Classical HVDC using thyristor-based 12-pulse converters for long distance transmission. So that's existing relatively mature application of power electronics. That's transmission, obviously. That's at the transmission level. At the distribution level, we do reactive power compensation, and then you can also put that, at the district transmission level. So that's so-called a STATCOM, right? STATCOM is part of it, but the application was very limited. Most of that applications are on the consumption side. So you recognize the electronics, the computers, the motor drives, the variable speed drives, using industry process. The diagrams above the at the top shows the circuit, what we call topologies, that goes in behind these applications, right? So at the consumption side, a lot of the single phase loads require rectify in the front, and then you get, DC-DC converter regulated. So these are the applications of power electronics in power systems up to, I would say, 15, 20 years ago. It's limited mostly on the consumption side. Some application at the distribution transmission level, but certainly nothing at the generation side. So if you talk to power system colleagues, right, they know a little bit about HVDC, but they really don't care about everything else, right? For power system stability is, you have these large generators, you got the transmission network, and you have relatively simple representation of the loads, right? The lumped PQ loads or Z loads, whatever, right? You don't really get into the actual characteristics of the converters behind. So power system people really don't care about it until recent years. That has really changed in last 10, 15 years. So technology-wise, we're still using most of the same converters that you saw on the previous page. So fundamental technology hasn't changed in power electronics. They're more or less mature. The only addition we have in terms of converter design is what I showed on the lower left bottom. It's called MMC, the modular multi-level converters. So these are really developed for power system applications, for high voltage. So you put like hundreds of these modules. So you see here in the diagram, you see 3 modules, right? Each module has 2 semiconductor devices and 1 capacitor. That's 1 module. You build that module, it's like a size of maybe a few desktop computers, but you stack 200, 300 of them to really build high voltage DC link, because each module can handle maybe 2 kilovolts. But in high voltage DC transmission, we talk about several hundred kilovolts. So you put many of these modules in series to form that converter. And this modular approach is really attractive because it gives you the redundancy. It makes the manufacturing very easy. So that's a new development that become mature in the last 10, 15 years. The rest of the converter technologies are more or less the same. What's amazing was the application. So you saw all the pictures, and you recognize, I think, most of them, right? So the most fundamental change, I would say, is the penetration of power electronics into the generation side, right? Generation of electricity from wind and solar. And these are not small, like, we're not talking about small rooftop PV inverter on residential home. It's small. Power system people don't really care about that, right? That's so small. But now we're really building large wind farms. We're really building larger wind farms. So you talk about hundreds of megawatts of wind farm, and they are comparable to larger power plants. And some of the PV farms also reaches hundreds of megawatts, right? So that's really interesting change. Power electronics now getting into the generation side. Transmission, there are more and more DC transmission for 2 reasons. One is a lot of the wind development, wind farms are in offshore. You go to Germany in the North Sea, go to UK, a lot of the wind farms are offshore. And for offshore transmission, you use cables, right? Submarine cables. And the cable capacitance severely limits the amount of power you can transfer over long distance, right? The capacitance discharge and charging current just takes away the capacity of the cable. So if you have more than 50 kilometers of distance, then AC transmission becomes really difficult and less efficient. So a lot of the offshore wind projects in Europe, in Germany in particular, are based on DC transmission. So you build like a dozen HVDC transmission in Germany. And for onshore transmission, it's similar because when you develop larger scale wind, you go to the places where you have the best wind resources. But that's typically not where people live, right? So you have to transfer electricity over long distance, and DC becomes necessary even for overhead transmission if you go over long distance. So HVDC comes, it's kind of a twin. In some parts of the world, people say HVDC and renewable development are kind of twins because they come hands in hands. And so that's on the upper left side, the generating transmission. You recognize this battery storage. I don't know how much of that has been discussed in Turkey, but in US, in Europe, energy storage becomes really important because when you rely on renewables, the intermittency, the variation of renewable production becomes very problematic. So to balance that variation, you really need to use storage. So there's a lot of larger scale energy storage projects in US, for example. I know there are several 100 megawatts of energy storage projects that are going on. So that's you can call that, it's not really generation, right? But it's part of the network. So it can be transmission or distribution. It helps to operate the system. On the consumption side, we certainly have more and more power electronic, because the electrification, the electrical vehicles, the more electronics. So the picture I'm pointing at with the laser, that's a data center. I've been working with Facebook in the last 3-4 years. I don't know if you heard about these, but everything we do, Zoom, whatever, Uber, anything you rely on, it goes to data centers. And these data centers, individual data centers, will consume somewhere in the order of 100 to 200 megawatts, single data centers in the couple hundred megawatts level. Now we talk about 300, 400 megawatts power. And you look at, all the power goes into a data center. It goes several stages of power conversion before it reaches the server. Because the server needs like 1 volt, right? 1 volt, 2 volt. That's where 90% of electricity is consumed. But you come in, the electricity comes in at the 110 kV, right? So from 110 kV to 1 volt, it goes through a number of power conversion stages. Enormous amount of power electronics. So my point is, all of these is pointing into a future where, the power system will become dominated by power electronics. And that's a really interesting development. It's going to be a really different power system also. So just to add to that, I'm looking at why Turkey is here. Yes, I saw Turkey is on this table. So these tables summarize the countries that have made commitment to reach carbon neutrality for the entire economy, right? So that's a really aggressive goal. Many countries are targeting at 2050 or 2060. So between 2050 and 2060, the global economy is supposed to become carbon neutral. It's not carbon free, but in sectors where we're producing carbon, we need to sequester or absorb carbon in other sectors. So the whole economy becomes neutral. And that's a really aggressive goal, but it's really serious matter now. It's about global warming and climate change. The other table I listed here shows the different states in the US that have committed to achieve carbon-free electricity. By most of these will happen in the next 2 decades, right? So looking at the time, it's like between 2040, 2050, right? So that's only 20 years from today. We need to decarbonize the entire electrical power sector. How do you do that? Well, you cannot burn gas, oil, or coal to generate electricity, right? So we have to transit the power grid into renewable based in the next 20 years. And the table on the bottom, the chart on the bottom. So some companies, some countries are more aggressive than others. So the ERCOT, the Texas Electric Reliability Council of Texas, ERCOT, is one of the industry partners we work with. They will have 50% of electricity produced from renewable energy in the next 2 years. It's already 50-50 now. And some of the German companies set the goal to reach 100% renewable by 2030. So you talk about less than 10 years from now. Globally, we're looking at 20 to 30 years. We have to go from today's carbon sort of dominated electrical system to renewable system. And that's a tremendous transformation if you think about what has to happen. So going back to this chart I showed you before, obviously the system is going to be more complex. So we need more power system engineers who understand the complexity of the system and can design and operate this much more complex system in the future, right? But technology-wise, power electronics is the key enabler for that. Because now every watts of electricity has to be processed by power electronics, right? Before they can go into the grid, you get converters. And before you can use it, you have converters. So if we talk about 100% renewable for the future, for carbon-free electrical system, we're really talking about more than 100% converter-based power system, because often the power has to be processed more than once by power electronics, right? So you count the megawatts of capacity, right? It's much larger than the capacity of the system. So this, you probably have heard a lot of these discussions already. It's a global transition, what we call, now called energy transition. And for power electronics engineers, it's kind of exciting to, have the opportunity to work on these hardware, making turbines, making PV inverters, making HVDC converters, because you have to make those converters, right? Hopefully we don't run out of silicon for that purpose, right? It's a great opportunity for power electronics engineers, but from research standpoint, a lot of the converter technologies are mature, as I mentioned earlier, right? The converter technologies are mature. So my own research focus has been on the system. We still have the transmission line, we still have transformers, but we are replacing conventional generators by wind turbines and PV inverters, right? You got converters everywhere. So the design, operation, and the stability of the whole system becomes really questionable. If you think about how we study power system stability today, we have beautiful theory, we got all the tools, the mathematical models, they work perfect for several decades, right? We've been perfecting them, but now things are going to be different, right? Instead of generators, we're going to have converters. So how do you deal with that in power system? That becomes a really big challenge. So these so-called converter-based power system is becoming a really dominant discussion in both power electronics and power systems community. So the rest of my presentation will give you an overview of what that means from my personal perspective. And you know, I put these diagram here, and most of you know what that means, right? Because this, you know, this future power system is like the huge elephant, right? You know, we never saw these before, and we're just approaching it from our perspective. You know, my background is power electronics. We also have people coming from controls fields, power system fields. You know, we try to solve these problems, but you never seen it. So I'm really mindful of our limitations, right? We kind of, you know, try to touch it from different angles. So my view can be very skewed today, okay? But hopefully, you know, at least you kind of get my point of view, and then you can, you know, think about that critically and combine with that with your own background, and use that as a starting point, because I can tell you, this is an exciting field for the next 30 years. So I want to just go to the fundamentals, because the system is so complex, right? You can talk about that from many different angles, okay? But at the end, you need to go to the bottom line and go to the fundamentals in order to really sort things out, right? So these on the next page is kind of my effort to get down to the bottom of this problem and see how can we deal with that. So what I want to do is to discuss the fundamental difference between converters and synchronous generators. Because if you think about the system, that's really where things are going to be different, right? The transmission line is going to be transmission lines, the transformers are going to be transformers. It's really about converters replacing generators for generation. So we need to understand how converters are different from synchronous generators. So the first difference identified here is the speed of control. Okay, speed of control. In generator, it's all relative term. When we say slow or fast, it's all relative, right? But I'm using the term slow to describe the generator control relative to converter. So in generator control, if you look at the generator machine level, there are really two fundamental control functions, right? One is to regulate the excitation field so you can control the voltage. Right? The other is to control the speed, the prime mover, so that you can regulate the frequency, right? So these are two basic control functions: voltage control, frequency control. Each correspond to a physical quantity you regulate, right? Voltage control is the magnetic field, it's current control, and frequency control is the mechanical time constant, rotating speed. And both are slow in the sense that if you look at the bandwidth of the control functions, right? The voltage control, you may have a bandwidth of a few hertz, right? A few hertz is your frequency limit, the bandwidth. Speed control, on the other hand, because you're dealing with a large, you know, mechanical mass, the time constant is you know, in the order of seconds. So your speed is much slower. You talk about milliseconds or multiple seconds of control. So the bandwidth is less than 1 hertz. And by the standards of power electronics, these are kind of slow control, right? Now I know in power system you have even slower control, right? The inter-area coordination, you know, there are a lot of other slower controls. But these two generator level control functions are more directly comparable to what we do in converters. Right? So simply put, if you look at the control bandwidth relative to the fundamental frequency, you can say that the bandwidth, called the FC in machine control, is less than 10% of the fundamental frequency. Right, fundamental frequency 50 or 60 hertz, you talk about a few hertz or lower speed. So, you know, 10% or less of the fundamental frequency. On the converter control, it's the opposite, because in converters, we don't have these large electromagnetic time constant to regulate, like the big winding. We don't have these mechanical mass to control, right? So it's all semiconductor switches. And semiconductor switches can operate at kilohertz, multiple kilohertz, right? So we need these fast control to really perform the power conversion function. So the most inner function is to regulate these current and to give you the sinusoidal response, because you don't produce this sine wave like what we do in generator, right? This is all done by semiconductor switching, pulse width modulation. your modulating has to be much faster than the fundamental frequency. So to make it simple, the control bandwidth in power electronics, the inner loop, you talk about 10 times above the fundamental, right? So you put these next to each other. One is less than 10% of the fundamental. The other is 10 times higher than that. And basically you have 100 times difference in the speed of control. Now that is important for generator design, for converter design, but this is also very important at the system level, because now you have really fast dynamics you have to deal with, right? Dynamics far beyond the dynamics that we worry about in traditional power system. Okay, so that's one important difference, the speed of control. The second one has to do with the physical aspect of the machine. You know, in machines, it's basically copper and iron, and then insulators, right? So if you have a fault, I mean, fault is everywhere in the power system, right? If you have a fault in the system, you got a short circuit really close to the generator. The generator is going to drive a huge amount of fault current, 5 times, even 8 times fault current, right? You cannot do anything with it, right? It takes time to clear the fault. So during the fault, the generator will feed the current into the fault. And we rely on that to design all the protection and rest of the system, right? It comes with the generator. So the overloading capability comes free. And we design the whole system based upon that. For converters, well, you can do that. If you want to take 10 times more current, you can do it, but you have to put 10 times more semiconductor devices in parallel, right? Because every device will be rated for a certain current. And the time constant we talk about for the device to fail on the overcurrent is milliseconds, right? So you cannot put that much current through a semiconductor device, more than just a few microseconds. So to handle these large short circuit current, you have to put a lot of semiconductors there. And that's going to be really expensive to do. Not many people are willing to pay for that. In typical converter design, we rate the semiconductor devices for 20, maybe up to 50% overcurrent. Not 5 times, because that's not economical, right? Maybe 50% overcurrent. And if the actual current exceeds that, it's not a problem for the semiconductor device, because the device can shut down in microseconds, right? It will protect itself. It just simply shuts down. The current will stop, right? And that's an advantage compared to generators, because generator cannot stop that, right? Converters can stop it. That's fine for the converters, but that's going to be really problematic for the system, because today's system rely on the fault current to clear the fault, right? And to support the system during the fault. If we have all the converters operating the system, you get some fault somewhere, there's a glitch, all the converters start to trip. Then you're gonna have blackout every day, right? You're gonna have blackout every day, because all the converters just trip, right? And you have to restart, okay? That's certainly not possible, okay? So this is an important limitation of semiconductors, because we're really comparing semiconductors versus conductors and insulators. That's another fundamental difference. So I hope this gave you a sense for what we're really facing. It's not just some equation. This goes to the fundamental properties of the devices, the materials we use to build this system, right? And we need to live with this system, okay, in the future. Now, obviously, this is a really general problem. In research, we need to narrow down into something that individually we can contribute to, right? So with that as a background, I'd like to give you an overview of the specific research topic we've been addressing in our program, because this requires not just the whole community, but also, you know, more than one generation of engineers to tackle. It's not something we can solve alone, right? So we've been focusing in certain aspects, and this is more related to the first difference, the speed of control difference. Because if you think about system stability, right? Each of these difference kind of relates to a stability phenomena, right? If you look at the control speed, the dynamics, this is the more classical stability we talk about. It's what we call steady state or small signal stability, right? Because these are dynamic. You have to manage. You have to be able to operate the system. So the first challenge is how do you maintain small signal stability so you can actually establish a steady state operation and maintain that steady state operation, right? So this is small signal stability. In that steady state, you get some perturbation, you can return to stable operation, right? So that's mostly has to do with the speed of control, the dynamics. The second, overloading capacity of these problem protection. In power system, we call that transient stability, right? In control theory, we call that large signal stability. Basically, you have a fault, you got large oscillation transition, and you have protection, right? All the nonlinear behavior, you have to maintain stability. So there, broadly speaking, you know, we have these small signal stability and large signal stability to deal with, and each will have to deal with one of the fundamental challenges here. So what we have been focusing on is more the small signal stability related to the speed of control, because if you think about it, that's necessary. That's the first step, right? You have to be able to operate the system before you worry about the fault conditions. Okay, so that's kind of the background for the research we've been working on. So I want to now go to the small signal stability. You know, small signal stability, we often talk about that in the frequency domain, right? So frequency domain, frequency response is a very convenient tool to use for small signal analysis. So this diagram basically is looking at control functions over frequency. That's what you see on the horizontal axis. The frequency range. So going from subhertz, millihertz, to tens of kilohertz, right? So this is a very wide frequency range. Now, in traditional power system, we have different control functions. So these are what the blocks represent. The prime mover control that regulate the frequency, excitation control that controls the voltage, right? And these are the two basic functions we talk about. The positions of these blocks represent where the speed of control is, right? So the prime mover control is in the subhertz range, so maybe up to 1 hertz. So that's the upper limit of the dynamics, right? Voltage control may be a few hertz, right? So that's where the position of the box represent. The location of the box relative to the horizontal axis indicates the dynamic frequency range. Right? And obviously, these are all congregated in the low frequency range, right? Below the fundamental. And because of that, the stability phenomena we discuss in power system are also in that corresponding frequency range. So you talk about angle frequency stability, that's again in the subhertz range, right? Voltage stability may go to a few hertz, 10 hertz, right? And then the highest frequency phenomena we talk about is the SSR, subsynchronous resonance, subsynchronous oscillation, subsynchronous control interaction, you know, this SS stuff. That may go to 10, 20, even 30 hertz, depending on the mechanism. There are different mechanisms for that. But they're still below the fundamental, okay? They're still all below the fundamental. So because of that, this diagram on the, I just added here, you cannot read, but this is in textbook, in a lot of the standard power system textbook. It basically talks about power system stability. And you look at closely, all the stability phenomena we talk about in that diagram concentrate in this low frequency range, right? There's nothing at the high frequency range, right? The space above 10, 20 hertz is a wide space. There's nothing there. The only thing we worry about there is EMT transient. You probably learned that already, right? EMT simulation, right? So we do EMT study, EMT simulation, but that's not stability. It's not about stability, it's about transient. It's about protection, right? And safety of equipment. It's not about stability because we don't have active control in that frequency range in traditional power system, right? If you don't have active control in that frequency range, there's no instability to worry about. So everything works perfect with today's or up to today, the power system, right? The machines, the theory, all of that goes really well. But the converters are going to change that. So these diagrams show these boxes represent the control functions related to converters. So with larger turbine generators, wind turbine, we still have some of the mechanical time constant. So they kind of appear in the low frequency range. But now we are adding these fast control functions. These are the inner control functions of the converters. And they certainly, each individual loop can become unstable, right? So the power electronics engineers have to design them carefully to make sure they are stable. But their stability in an individual operation does not guarantee stability of the power system. You know that, right? A perfectly designed generator doesn't guarantee stability of the power system, right? So you need to take that into the system context. And that's the challenge we're seeing now. So in this high frequency range, because now we are adding feedback, we have control, active control, we have to worry about stability, okay? For the lack of better term, I call that EMT stability, electromagnetic transient stability, because it's like in the frequency range where we used to call EMT frequency, right? But now we have active control. So we need to address the stability of this new frontier. You know, I call that new frontier because this is a high frequency range where people don't worry about up to recent years. Now, I think for the lack of time, I'm going to skip the next couple of pages. But what I wanted to do, put on this page without going through the, let me just fly through this. I want to give you some sense for what we're talking about, because you know the fundamental understanding is summarized here, but it's kind of abstract, right? What does that mean? You know, you got this new stability. What does that mean? What does that mean to me, right? I get some examples. We built. So when I started this research about 15 years ago, I spent about $1 million. I built a test bed. Members saw that, and that was really the beginning of this research because you know I can predict these conceptually, but I wouldn't know for sure, right? So really to understand and see the problems, we built a test bed in the lab, a converter-based power system, and we actually did the experiment. And when you do that, all the problems start to jump out, and that is really what we kind of anticipated in the earlier phase. So these are the measurements from the test bed. So you can see the PV inverter. When you change the grid condition, initial measurement shows perfectly sinusoidal voltage and current. Right? That's the first chart you see there. When we purposely change the grid condition, so the inverter is the same, but the grid, the simulated grid in the lab changes, and let's start to introduce marginally stable oscillation, and you see that in the second chart. So these harmonics start to appear. They're not really harmonic, they are marginally stable resonance that creates these oscillations. And when we further change the condition of the grid, the inverter just disconnect because you cannot maintain stability. So the diagram here shows the inverter operates for some cycles, and because the stability is lost, the inverter shuts down and start over again, right? And that's kind of the problem we talk about. Inverter shuts down, and for a single inverter, you do that, doesn't matter. But if all the converters do that, then you know it's certainly not acceptable. So these are the kind of measurement we did in the lab. This measurement is taken in the German North Sea. So the company that I work with for many years now, it's actual recording of an incident in the offshore wind farm, where you basically incident triggered the recording system. So they have an automatic recording system. If everything is normal, the data will be erased periodically. But if there's an incident, right, abnormal operation, the data will be captured. So this is one of the recording. If you zoom in, what you see there is a growing harmonic. So initially this relatively clean, but then there's a harmonic that start to appear and then grow over some cycles to a level that is not acceptable. And this, from this zoom in view, you can see the harmonic. Right, so in the zoom in view, it's still small, but go to 20, 30%. And that becomes a major problem. So there was actually a major incident in the German North Sea because of this kind of resonance. It caused actually a fire in an offshore HVDC station. So you may have seen some of the pictures. I have actually a picture of that. One of the stations caught fire internally. So that burned down a large section of the converter system. And that's a major incident. There's also another recording I want to show you here. This is from onshore wind farm, larger wind farm area. That's actually the whole system has about 10 gigawatts of wind turbines. And this is a recording during a system resonance incident. So the big bar in the middle, these are the fundamental voltage and current, 50 hertz, right? And then next to it, on both sides, you see two small harmonic. They have the same distance with the fundamental. So they're kind of symmetrical, right? Right now they're small at the beginning, but this is a live recording. So when I show you that recording, you will see, let me see how I show that. You will see these two harmonics start to move, right? Start to move, grow, and eventually will grow to a level where the system shuts down and the recording stops. Right, so that's where the protection shut down the system. And this is very common. If you talk to people working in the field in the last 5-8 years, this become a very widespread problem. And you can call this subsynchronous resonance, but the fundamental interaction behind is the wind turbine and the converters doing that. Right. So this kind of shows, what this means in practical system. Now today, we don't have all these converters dominating the system. So the converters can still protect themselves, right? So they can measure these harmonics. And you can introduce certain software, you detect these, and when these harmonics see certain level, you can shut down. That's okay. But if this happens in the future, you got every converter, or the majority of the electricity comes from these converters, you just cannot do that, right? You cannot shut down the system. So we have to find a different way to deal with this. First of all, we need to prevent this resonance, right? Or prevent this instability from happening. So that's the kind of the theoretical side. So now you say, okay, well, all right, so we need to study this new stability phenomena, right? So it's high frequency. We didn't consider them before. Now we have to take them seriously. What's the deal? The control theory tells us you can do that in frequency domain, you can do that in time domain. They don't really care about the frequency, right? Whatever model tells you, it's where the stability is. Okay, so fundamentally, it's just stability, okay? But the challenge is we don't have the models, right? Because in today's power system stability theory, the models we use to study stability are based on the fundamental frequency model, the phasor model, right? You model the voltage and current by the magnitude and phase angle or the frequency. You don't use the 50 hertz instantaneous variable, right? We only use those variables in the EMT simulation. That's EMT models. Stability analysis, we don't use EMT models. We use fundamental frequency, RMS value-based models, right? And that's all these stability theories are based upon. But we cannot use those models for the high frequency dynamics. They're happening within every fundamental cycle. So your fundamental frequency model is not going to be able to capture that. We need EMT models. So the starting point for stability analysis in the EMT frequency range has to be EMT models, right? Naturally, you have to start with EMT models. Now, obviously, we can do EMT simulation, right? With computers becoming more powerful, we can do more and more EMT simulation, which is easy on one side, because you can easily start it, but it's extremely difficult to do well, right? Because if you just have one converter, you can simulate it, but you talk about millions of turbines, okay? How do you simulate them together, right? And you also need a very detailed models. The very detailed models of wind turbines and PV inverters. You need the manufacturer to give you those models. They're not going to give to you because that's their secret. EMT model is a secret to them. It's everything to them. You cannot get that, right? So it's academically, it's easier to do, right? I just make a generic model. I can show some simulation, but practically it's extremely difficult. And as you know, when we deal with larger system stability, we cannot just run simulation, right? We need to have the equivalence of today's, frequency stability, voltage stability theory for EMT stability. We need to have the equivalence of them in order to cover the high frequency stability. So that basically speaks to small signal frequency domain analysis, right? We need to do that and provide proper models for EMT study, but in the frequency domain and small signal. And this becomes a fundamental challenge because the models, EMT models, are so difficult to linearize. Do we have a limit on time? Okay. Okay. So converter model, if you haven't learned any of the converter models, every converter model is nonlinear. And because the operating with the grid, you got the 50 Hertz volcanic current going on, right? So the model is nonlinear and time varying. Okay. Well, if you think about mathematically, you have a nonlinear time varying model. We just don't have good control theory to deal with that system, right? So the only way we can deal with it is by small signal analysis. Okay, but the time varying operation makes it very difficult. Because if you linearize, that's the only equation I have here. If you linearize, try to linearize a nonlinear function called x times y, right? This bilinear term is very common, nonlinearity. You want to linearize that function, you can always do that by Tailor expansion, right? Everyone knows how to do it. You expand it if x and y each has a fundamental component plus perturbation delta x and delta y, right? Expand it, we ignore the high order term, you end up with three terms. The first term represents the fundamental steady state operation, so you don't need to worry about that. That's steady state. The second and third term represent the small signal response, right? Each is proportional to your disturbance. So that's small signal response. It's linear for these small signal perturbation, delta x and delta y. But the coefficient we have in front of each of the linear term is time periodic, right? That has 50 or 60 Hertz fundamental. That changes at the fundamental frequency. So this linearization gives you a linear model, but with time periodic coefficiency. So you end up with what we call LTP models, linear time periodic models. And if you recall the control theory, right, the Laplace transformation, Nyquist criteria, Bode plots, all of that can only be applied to linear time invariant models, LTI models, not LTP models. So yeah, yes, it's easy to get these LTP models, but no control practical engineers know what to do with it, right? So that becomes, from actual practical challenge now, you face a mathematical problem. Now we are engineers, we're not going to be able to reinvent mathematics to solve that fundamental problem. Right? So we need to get around that and find a way to do small signal analysis without the LTP type of characteristics. So that's kind of my research focused on in the last 10 years. Theoretical, that's one of the areas. So in a short form, I'm going to try to go through these quickly. In a short form, one of the fundamental aspects of our research is to develop linear time invariant models by a different linearization method, what we call the harmonic linearization. And you can call this an extension of the describing function method. Okay, so instead of assuming an arbitrarily perturbation of delta x and delta y, we introduce a perturbation in a sinusoidal form. Right, so this is the fundamental, and then on top of that, we introduce a perturbation also in a sinusoidal form. So this perturbation has a specific form; it's a sine form, has a magnitude and phase angle, and with that perturbation, our interest is to find the response of the system. So if I'm perturbing the voltage, right? So the voltage has a fundamental and then this small signal perturbation at certain frequency. What I'm interested in is the response of the converter or the system to that voltage. So I need to find out the corresponding current component, right, in the response, okay? So I inject a voltage and I measure the current at the same frequency. And that same frequency component gives me a transfer function from the voltage to the current, which is, as we know, it's impedance, right? It's impedance. Voltage divided by current is impedance. But this is done directly in the frequency domain. So instead of delta x and delta y, or delta I and delta v, right, we work directly with a sinusoidal perturbation. It's kind of extension of the describing function method. But if you recall that, the classical describing function method is about a DC operating point and add a sinusoidal perturbation to that, right? Here we have a sinusoidal operation, and then we add another sine wave to that. So it's a kind of this extended describing function method. But that's how we model converters. We use these voltage perturbation to develop the small signal response of every converter. And that is essentially impedance. So that's part of the theoretical study. The second part is, if you recall the stability theory in power system, we don't use impedance, right? So with the impedance model of the converters, we also develop a framework to study system stability based on impedance. The idea is actually very simple. If you have, just in the simplest form, if I have a single converter, this can be a wind turbine, can be a HVDC converter, right? Connected to the grid. Now, if I model each part of the system, so the system has two parts, the grid and the converter. The converter can represent wind farm, actually, because a wind farm, you can aggregate multiple turbines together by series parallel connection, they become one impedance, right? So you can use that against the grid. So it's a simple system model with two components. And if I model each side by impedance, so the grid can be modeled by a 70 equivalent circuit, right? Ideal voltage source behind impedance. And then converter modeled by admittance or impedance in parallel with the current source. But the converter can be modeled as a current source because today, most converters are controlled to inject current to the grid. And that's what we call a grid following converter. They accept the grid voltage and they inject current into it. In the future, we have to model this differently, but it's still impedance. With that simple equivalent circuit, you can find out that the dynamics, the stability of this network, the circuit, is equivalent to the stability of this feedback loop. Right? The forward gain is the impedance of the grid. The feedback gain is the admittance of the converter. Mathematically, these two are equivalent. Right? So that's how we relate the stability of a power system to a stability of a feedback loop. Now, when we connect these converters to the grid, we never think of a feedback, right? But mathematically, because impedance, they actually form that feedback effectively. And as soon as you see that, you know how to do the stability analysis, right? This is a feedback loop. Every EE student knows how to do stability analysis of that. Just apply Nyquist criteria to that, right? So everything else becomes like routine. But the key is to have these two theoretical pieces, right? The component model you develop for individual converters, and then the formulation of the system stability model using that impedance. Once we have these kind of system level model, then the rest is control application. So that's most of our research focus. So this is a summary of the work we did. We did a lot of modeling, impedance modeling of different converters, PV inverters, wind turbines, HVDC converters, fax devices. So a lot of analytical modeling. And then use of these models in different system stability studies. Up to recent years, most of the applications are based on this simple formulation, what I call these single converters. So by aggregation, we can also model a larger wind farm in the same form, right? But the system model is basically that single input, single output feedback loop. That's the final form of a model, right? Very simple. We use that to study stability of different renewable energy systems, HVDC transmission, and then obviously we look at the design control of converters to mitigate the instability, because our goal is not to just to analyze it. Our goal is to stabilize it. But once you understand the models, the dynamics, right? For power electronics people in particular, I can come in, I can change the controls, I can retune the control. It's relatively easy to stabilize once you understand the root cause of that. So that's our research summary. Now, there's a lot of exciting development in the last 7-8 years. I want to share with you some of the practical experience, but for time limit, I'm going to skip that. So I've been working with a lot of these companies internationally in solving those practical system problems. And these are some of the examples that I want to explain, but I'm going to skip that. So this includes like offshore wind with HVDC transmission, onshore renewable system, larger data centers, talk about 200 megawatts, the instability and resonance in all of these systems. It's very interesting challenges. So I work with them closely. And beyond that, now I think there is the recognition. So 10 years ago, when I started to talk about these, not many people really appreciate it because nobody has seen those kind of problems, right? So the reaction normally, when you talk to people in room, power electronics people like it because they think this is an interesting way to do research, write papers, okay? Industry people say, oh, nice theory, but we don't have the problem. That's 10 years ago. I never heard that comments anymore these days because now the problems are kind of everywhere. So we had some very interesting experience. This is some recent development. So now we start to see converters all over the places. So that single input, single output formulation is no longer sufficient. We have to deal with multiple wind farms, multiple HVDC converters at the same time. So this is a different way of formulating the system model. So you got a grid and you got a multiple HVDC wind farms connecting at the same time. So the mathematic model becomes a multiple input, multiple output feedback loop. But it's, it's again, just mathematical generalization. We have that. So we're ready to tackle those problems. I'm going to skip the next few pages and maybe just summarize these and leave that page here. So going back to the two fundamental challenges I mentioned, or difference, fast control versus slow control between machine converters, and then the overloading, right? So each is closely related to some stability phenomenon. Fast control is mostly related to small signal stability, which is what we've been focusing on. I think we have a solid foundation now to tackle that. Industry is kind of catching up, and hopefully, this will become a standard practice. we start to look at into the large signal aspect, the fault conditions, because that's important in power system. But we really haven't done much. So that might be something, you know, particularly for those who are interested in transient stability, this might be time to think about it. But in general, I think next 20 years, 30 years will be exciting because we really talk about transformation of the entire power grid. So ironically, I'm going to leave that page here. So if you study power system, if you go in the old days, you know, what we call classical power system stability theory, these are the kind of, you know, classical papers. I don't know how many of you have read them, but they're like, you know, 1920 papers. They really established the existing power system theory. So from 1920 to the end of Second World War, 1950, that's about 30 years. That's when the classical power system theory was developed and become mature. I would argue, you know, after 1950, we continue to make improvement, but it's mostly in the tools, right? In the, you know, computational tools, communication. So more the electronics, the information side of the grid. The fundamental theory of power system was established in that 30-year time period. Interestingly, 1 century later, right, we're again in the 20s, right, of 21st century, we sort of have to reinvent it. Not from scratch, because, you know, we still have this low frequency dynamic we have to deal with. So the existing theory are still needed, but we need to cover the other part of the spectrum. And you look at the time frame, you're going back to the earlier page I showed, by 2050, 2060, we need to decarbonize the entire economy, right? So by 2040-ish, 2050, the grid should be mostly renewable, if not 100% renewable, right? So 100% or 80% converters. So we got about 20, 30 years to do that. And that's exactly what taught for earlier generations who did their job. So I think that's kind of your job. You know, I'm not going to be working for 30 years, right? But someone has to do this, and hope one of you can make contribution to this. That's my last page. Thank you.
Thank you very much, Jan. It was actually a nice meeting, a nice presentation, both for the physical audience, also for the audience in the Zoom site. And we may have some questions, actually, and whoever would like to listen to it will already watch it from also YouTube rotation of it. So, first of all, there's a question from the chat. Is the silent power factor software enough for EMT modeling for the simulations? Any suggestion for this?
Can you repeat the question?
You also can see it in the chat screen, but one of the audience from the Zoom side asks that is Dick Silent Power Factory software enough for EMT modeling for these simulations?
I see. That's an interesting question. Yeah, so I've been working with these software companies for last few years. So I have close relationship with this Canadian company called Opal RT Lab, and that's a EMT tool, mostly for real-time hardware in the loop simulation. You know, we are also really close there in Montreal. You know, it's about 3 hours drive. I've been talking to Power Factory of the company DigiXisland for a few years as well. And in fact, about a month from today, I've been meeting with them in Germany. Yes, so yes, we need these tools. I think all of these tools, or most of these tools are useful, but I would say none of them is sufficient for what we need in the future. So we need to work with the software industry to do that. It's more than simulation. So what we need is really simulation and small signal analysis in the same package, because simulation alone will not be able to, I mean, no matter how powerful the computers are, you are not going to be able to simulate the entire power grid with millions of turbines. You just cannot do that, right? EMT simulation is just impossible. So we need to supplement EMT simulation, integrate that with small signal and other analysis. And that's, I think, the next phase of the develop. So we got the theory, we demonstrate applications, often with MATLAB calculation, but we need to automate that. For power system application, we know all the technologies at the end, right? For converters, it goes into converter manufacturing, right? So that's the industry we work with, transfer technology to them. But for system model analysis, you have to turn that into either specification and grid codes, right? So it becomes standards and people can follow. And then the others is tools, computational tools, software tools people can use. At the end, you have to give these to people, not just papers, right? Because practical engineers cannot just read papers and then do things. They need the tools to do it. So I think the next 10 years will be interesting for that too.
Especially for the software side, I agree
Yes.
with you, because whatever we call as a classical power flow will already have also a change regarding the far more improvements in the DC transmission. And whatever we do is a full AC power flow, and whatever we calculate as a voltage, magnitude, as angle, will have a different overlook when we look at from the DC side. So
Yes.
we should have mixed power flows, and mixed power flow means whatever you call is in the optimization side, maybe you will have inputs like if this is DC or AC, and if we can skip this equation for the DC side and we can continue with the AC side, and all software we need, and all softwares already depend on the basic power flow equations, so that all softwares will need adaptation if we have commerce in with the power system operation.
Yes.
And I don't see any question in the share side, but if the audience, physical audience, has some questions, I would be happy to direct it to here. Yes, you can even come here and ask. By the way, Jian will can hear it, and also the audience will hear it. Yes, by the way, the Zoom audience can also hear. Okay.
Hello, everyone. First, thanks for your presentation and coming here. I have an answer question about the semiconductors. What do you think about the gallium nitride semiconductors in the power systems and relations between the power electronics?
Yeah, that's a good question. I didn't get much into power electronics, but semiconductor devices, what we call wide bandgap semiconductor devices, are certainly a very exciting development in recent years. So, we talk about silicon carbide and gallium nitride. For power system application, I think silicon carbide has more to offer because it's better for higher voltage, right? So you can go to kilovolt. So we talk about 10, 15 kilovolt silicon carbide based MOSFETs now. You can get samples. So that will simplify converter design for high voltage, because now you need less devices, right? Individual device can handle high voltage. We try not to rely on that today with this modular design, because with silicon you can get a 3 kV device. They build a module. If it's truly modular, you can stack many of them. So you are not limited by the individual device rating. But high voltage device will certainly help you to simplify that. So that's silicon carbide mostly. Gallium nitride is more useful for low voltage. So for that, basically we're talking about transportation, for example, because gallium nitride, the major benefit of gallium nitride compared to silicon is the fast switching. And so you can switch at a higher frequency. Now for grid, often we don't need high frequency switching because you have fixed 50 or 60 hertz, right? If you can switch at a couple of kilohertz, that's enough. You don't need to go to 10 kilohertz, 20 or 100 kilohertz. Is not necessary, and the benefits of high frequency switching is to reduce the size of the passive components, right? So the filters, the capacitor inductors become proportionally small if you increase the switching frequency. But for a lot of grid applications, you got to land. You don't need to shrink things, right? If you make them small, the heat removal becomes a problem. But for other applications, for transportation, for example, right? Making things small and compact is really important because you're carrying them with you. Okay, so gallium nitride, I think, has most benefit in those kind of applications. Transportation is probably the most important application today. And laptops, these can also benefit from high frequency, but transportation is mostly significant.
Thank you very much. Any more questions from the audience? I have the last question, actually. To talk about the demand side, the use of power electronics increases very much, especially with the introduction of the electrified transportation and other issues, and their power capacity levels increase a lot, especially when we talk about the fast charging issues and but when we talk about it, we know very well that the distribution system side is the weakest point in the electric power system operation. What do you say about the power quality impacts of these power electronics equipment when they even increase more in the consumer side?
So I think there are probably two parts to look at. One is a lot of the power quality in the traditional sense, where we basically consider these electronic loads as harmonic sources, right? So they're nonlinear, they create these distorted current. Although, with the latest technology, that's really minimal. But the impression, is, these loads create harmonics, and they can be amplified in the system and become a power quality problem. I think that's will continue to be the case. I don't think the situation will get worse. The technology will help to reduce the harmonic in the first place, because if you measure, they're dirty rectified, but you measure a lot of the products sold in Europe, right? They're very clean. I work with Facebook. The power supply, you measure the input current, is really clean, actually, very clean. So I think that problem is not going to get any worse. Now, if we generalize that power quality problem, because I taught this power quality class at RPI. So, you look at power quality, it's many different aspects. You get, voltage distortion, voltage fluctuation, intermittency. So in a broader sense,
mainly focusing on the harmonics, actually.
Okay. Yes, but in the broader sense, if you think about intermittency of production, that can create quite frequent voltage variation, and that can be part of the power quality issue, and we need to deal with that. The last point I want to add into that is even the harmonic, because of the history of this nonlinear behavior, the distortion, when these resonances start to appear, the first reaction people had was, oh, that's power quality problem. Well, it's actually not. It's instability or beginning of instability. So that problem is going to be worse, because the fundamental problem is these converters, they have the control. The control creates negative damping. So if you measure the impedance in the harmonic frequency range, the impedance has negative real part. Okay. Well, that negative real part, if it's negative enough, it will eat all the positive damping you have in the network, and you get an unstable resonance somewhere. And that will create a harmonic. So you don't have to have pre-existing harmonic to be amplified. That resonant, unstable resonance was, so a lot of the pictures show where initially you have really clean waveform, and then harmonics start to grow and grow. And that's really the reason. Under certain conditions, the negative damping becomes dominant. And so you have an unstable resonance, and that manifests itself into a growing harmonic, and that will shut down the system.
It's a hiding danger, actually.
Yes, and that can be mistaken as a power quality problem, but fundamental, that's a stability problem. So you cannot try to fill that out, right? It's not a current source. You can just fill it out. It's being created. Yes. So you have to modify the dynamics. You have to modify the impedance to damp the resonance.
Thank you very much, Jan. And First of
Thank
all,
you.
I would like to thank everyone who has participated in this great talk, physically or electronically. And we were very glad to host Cihan with the aid of our graduate student.
Son sözleri
Yes.
söyleyeceğim.
And many thanks to Professor Mehmet for helping us to host this great event. And the last words will be with Professor Murat.
On behalf of my university and the Graduate School of Science and Engineering, I would like to also thank the Professor San for accepting our invitation for the grad talk. And I would like to see you all for the next week. We will be talking about the food engineering for the next week's seminar. Please like and subscribe our social media. Thank you, everyone, online attendees.